piece of cake. Okay? The only thing to remember is that right angle at the entry. So, let us now look at velocity and acceleration. Of course, for the slider crank mode of operation, right? We don't want to spend time on the journal bearing operation because the output is not moving. Okay? So we go back to this picture, and of course, we need to understand that the picture is for 4-station Geneva wheel, but similar picture can be drawn for an arbitrary number of stations, just the beta angle is then different. So this is the mode of the pin engaged in the slot. So we need to use this triangle to find the relationship between the input, which is capital theta, this is the driving wheel, and the output, which is lowercase phi, which is the angle of the star wheel. Okay? When we find the relationship from this triangle, then we will proceed directly to differentiate to get velocity and differentiate again to get acceleration. And this will then save us to consider in some detail the dynamic behavior of this mechanism. Okay? So, how do we deal with this triangle? So now we are doing a kinematic analysis or position, velocity, acceleration, so we have already designed the mechanism. So we know the dimensions, so we know this, we know the radius, we know the distance, and we need relationship between input angle and output angle. So we are using this triangle, and let us start with something that I like a lot, the sine theorem. Okay? The sine theorem says that for a triangle, this divided by sine of this angle is the same as this divided by the sine of that angle, right? So we have our sine theorem, and therefore we write it as here as equations with one star. Now, the second equation is produced by projecting x and r on D. So R2 cosine theta plus x cosine phi equals to D, right? Of course, we also know that D is related to R2, which is this one, by the equation which we know from the design, that D is R2 divided by sine of pi divided by the number of stations. Okay? So now we are having two cool equations with two unknowns, theta and, the theta is, x and phi, because theta is the input. So theta we assume is known. And x and phi are unknown. So x is this one, and phi is this one. So we have to solve it. Now, I have a solution by hand, probably no mistake, but I also have a Mathematica file that solves the same stuff, which is already on LMS, okay? And that is almost certainly correct. So we find the tangent of phi this way, so we get this relationship, and of course you can see that this relationship in blue does not contain dimensions anymore, okay? Which is to be expected. The angular relationship is fixed by the requirement of the pin going into the slot at the right angle. And then the dimensions are only scaling up or scaling down the size of the mechanism. So if you have only the relationship between angles, you will expect no dimensions, and this is what you see. Just angle depends on angle and the number of stations, which defines the geometry of the system. Okay? So we get the red one is the solution for the position. Then you take the derivative. If you are lucky and no mistake, you get green. And then you do acceleration. And I am not even attempting to do it by hand, but I have a mathematical file.